Hello and welcome to this, the 7th in my series of videos, all under the umbrella title of Absolute Relativity. And as you can see, this one is on the measurement problem, and I'm going to try and keep this brief because I believe we've already solved this. There is no problem. Just simply by looking at quantum measurements, quantum effects in terms of interactions between protons with no subatomic particles, then there is no measurement problem. And just let me start off. I'm going to read directly from Wikipedia. In quantum mechanics, the measurement problem is the problem of how or whether wave function collapse occurs. The inability to observe such a collapse directly has given rise to different interpretations of quantum mechanics and poses a key set of questions that each interpretation must answer. The wave function in quantum mechanics evolves deterministically according to the Schrödinger equation as a linear superposition of different states. However, actual measurements always find the physical system in a definite state. In effect, it is that the wave function can be everywhere, but breaks down into a point particle. How is that? And quite simply, I'd say we've already answered this. I'm going to return to the very first video, and that was on Young's double slit experiment, and this shows absolutely, here's our light source. It's showed in all these different colours mixed together, so effectively you're going to choose a single colour just to simplify the light that's going through this system. Anyway, it's going through the double slit and reformed into here, and it reformed into the two waves which interfere or join together, and you get your interference pattern. And the problem occurs in looking at these wave functions that break down into individual particles. The difficulty in seeing what's going on has been the fact that we look at light particle, the photon. We look at the photon as being a particle. So a particle exists, is going through this system. We don't know which of these, and all of the, if you want to have a lot more on the double slit experiment, go back to video 1, but I say there is no photon particle. What you've got is an excited atom here, and it is setting up its wave function. Its wave function has been reshaped through here. Most of this, you've got these billions of atoms here. Most of them are going to react to the screen here. Some of them, because the screen is already lit, as it were, some of them have got nowhere to go. So they go through here, be reshaped, and end up with the single wave interfering with itself. So you're looking at a single particle here. You've got a complex wave pattern here that's been reshaped here, and you've got a screen here. It's a photographic screen that will that has its individual particles, so that whichever individual particle is susceptible, is ready for excitation, it will a direct response from this atom to this atom or this atom. And of course, the atoms that are ready to receive this, ready to respond, are random. So what you'll see is a random pattern that builds up into the interference pattern. And so we have no point particle. The wave doesn't break down into a point particle. The wave is the excitation of these individual atoms here, transferring its excited energy into these responsive atoms on this side. And we see that. Let's say our measuring instrument here is our eyes. That's our measuring instrument. So this extra light that we see in the light parts here, the light parts, we see them. So our measuring instrument in this case is our eyes. And now, this has led to the first, it's indirectly led to the first nonsense, what I call fairy tale physics of human consciousness being something to do with the results of quantum effects. There's nothing to do with the quantum effects, human consciousness. These light particles we see because this light is setting up a photon that's going to end up at our eye. But it may well end up in a dog's eye. It may well end up responding to another atom. It's nothing to do with us. We just happen to be there and have a look at it. We are the measuring instrument in this case. We've seen before in my previous video that when we do measure quantum systems, the measuring instrument, where the measuring instrument is, where it's coming from with respect to the system that we're measuring, does have an effect. And of course, what I've shown before is that in a quantum system, the protons are moving at different energy levels. So you're not going to catch it. You're not going to be sure of where it is, and you don't always measure an atom at the center of the atom. You can do if you're lucky, but an atom is a fuzzy thing. It's an energy, so that you can measure that energy in different places. It effectively doesn't have a border. So that there it is. different interpretations then is that another interpretation is the many worlds theory, which to me is the apex of fairy tale physics. This one says that this photon, these particles, these photons going through this system, they break down. The wave function of that particle doesn't break down at all, but just breaks down in our universe, this universe where it did break down, but there are then simultaneously created another universe where it doesn't break down. Right. Okay. Now, I'm sorry. That I'm astonished that the many worlds theory. I know people love the fact, you've got alternative universes and the multiverse and all this kind of stuff. They love all that, but essentially, come on. Everything, we are here in Hilbert space, in our 4 dimensions. I'm not even going to cover string theory. I don't need to, because all I need to say is 12, 16, 24, 124 dimensions. All these dimensions that string theory insists on having to make it work. I'm not even going to bother with it. I've read Brian Greene, and I have to say that the idea of and it's very, very clever. It's brilliant. The mathematics is way beyond what basically anybody could understand, because they have to computerize everything. But then you've got a hypothesis in string theory, and a mathematics is produced around that hypothesis. And when the mathematics are fed into a computer, you have, if the hypothesis is correct according to that mathematics, you have an expected answer. And when you get that, it's considered as proof. As a circular argument. The hypothesis itself of string theory is wrong. We don't need anything other than space-time. Hilbert space-time. 3 spatial and 1 time. That's it. That's all we need. So, Copenhagen interpretation was that the particle is in a superposition of states. It could be anywhere. Well, it couldn't be anywhere, because there is no such thing as a superposition of states. What you have is this particle and the wave function of its excited energy transferring to here. And as far as these particles are concerned, this is instantaneous. It's only us viewing the system in our space-time. We see this as time. We see this as the wave evolving in time. The wave doesn't evolve in time. The wave just is. It's all around here instantaneously. Between here and here, from light's point of view, there is no time. So there is no particle. There is only excited protons, excited particles in the source and in the receiver. Another idea that has come because of this is that the wave itself has information that we haven't seen, that we haven't measured, and the wave itself tells the particle where to go. So we have these hidden variables. Again, in my explanation that there is no particle, it's not necessary. Also, this hidden variables thing. I'll just revisit again one of the previous videos, quantum entanglement. So we've made you have these two, let's stay with photons, two photons, one polarized in this direction, one polarized in this direction, and here is a source, and when we measure this one, we find it's polarized in this direction. We know, whatever this distance is, that this one is polarized in this direction. So if we measure this one, how does this one know to be in this direction? And again, the hidden variables thing, there's something in this that we haven't seen that will tell it what to be, because this isn't decided. The polarization of this is not decided until we look at it. Mark that, when we look at it. It's not us looking at it when it reacts with something else. We shouldn't be saying when we look at it. It's not that us looking at it. It's when it reacts with something else, with another atom. And that may be our measuring device. It may not be. But let's say it is our measuring device and we see it's there. It's not. Its polarization is not determined until then. So how does this one know? So again, there's this hidden variables. There's another code in there that we haven't discovered what it is. I say no, of course not. What's happened is we've created these two photons from a single atom, and they're both at the same energy. I'm going to do a later video on creating entangled photons, but they're both at the same energy, and you can get that within a complex atom. And all that's happening is they've both set up their waveforms. So if they're both at the same energy, one is polarized in one direction, one's polarized in another. And now, if we measure one of them here, one waveform collapses, leaves the other waveform to communicate here. No hidden variables. And us looking at it is neither here nor there. It's not to do with human intervention. We could create these, and entangled photons were created in nature, and they will react with other. This atom will react with other atoms in different places, whether we observe it or not. That has to do with us. But this whole superposition of states thing is it's not so. There never is a superposition of states. There was only excited atoms. That then leads us let the nonsense surrounding superposition of states led Schrödinger. You know what's coming next. There he is, Schrödinger's cat. Yeah. You can see him there in waiting to be killed or not. And you may know this this inequality. It's the uncertainty, and it's all to do with we don't know where the particle is, etc., etc. We can't tell where the particle. There isn't a particle. We're going to be unsure of where it is until we measure it, until it reacts with something, and until we can find out where it's reacted with something. And Schrödinger is so many people think that Schrödinger was actually suggesting, he puts his cat in the box, and there's a nuclear reaction of a quantum reaction of some kind. He used a nuclear decay of a particle, and then a Geiger counter, let's say, that then if it goes off, and he looked at it in a box with what do you say, with nitrogen-13, which has a half-life of around about 10 minutes. So you look at it with 10 minutes, and the whole system is in a superposition of states. After 10 minutes, there's a 50-50 chance that nitrogen-13 is decayed. And if it decays, then it breaks a vial and poisons the cat. The cat dies. If it doesn't decay, the cat's alive. Now, Schrödinger used this to show that the superposition of states is there's something wrong with it. That's what he was trying to show. It doesn't transfer to the macro world. He's saying, of course, the cat. What Schrödinger was actually saying, of course, the cat is not in a superposition of states. It's not dead and alive. It's dead or alive. It's one of the two. And he was just trying to show that the Copenhagen interpretation of quantum mechanics was somehow wrong. And I have shown in all these videos how it's wrong. And it's wrong in looking for subatomic particles, because they don't exist. And as soon as we accept that, all of these problems, including the measurement problems in quantum mechanics, they evaporate, including the measurement problem. And then Schrödinger's cat, he's quite right. It's absurd. Of course it is. I've got to finish just by restating that there is no superposition of states. And that's it. My next video is going to be on the nature of the proton. I've done the nature of photons and electrons. I've shown that the Higgs boson is not necessary in any explanation of the mass of particles. It's just not necessary. I've shown that so far those subatomic particles have no independent existence. What I want to do is to go on and get a better description of the proton, and from that to show that we don't need any other subatomic particles. Okay, big claim. So I hope you'll join me in the next video. Okay, thank you and goodbye.